low. Is this working? Yeah, it is. Oh. All right. So let us continue today. And today what I will try to talk about is, so, there's all these questions always, how far can you trust the supernovae data? There's all this calibration business and standardization business, which may work better or worse. There's some scatter always in it. How, especially at the beginning, there was no real certainty that this is really that something like this is really correct. Then there's this possibility that the supernovae, in fact, are evolving in time. So they're not actually the same as a function of redshift. The universe is changing. So possibly that's leading to this, biasing your measurement of the parameters of cosmology. And third option, so very early on, people were wondering about that. It's called the tired light hypothesis. Actually, maybe something happens to the photons. They interact with something as they propagate through the universe, and there are these ideas for models where there are some particular axions, so the photon can just decay as it propagates in the presence of a magnetic field. So people are thinking maybe we're seeing this kind of luminosity distance be larger because actually we're just not seeing the full flux of photons. So that's all gone away, and it's gone away because we're capable of exploiting this duality of this angular diameter distance. So I will talk a bit about that, and essentially the measurements of distance we have today are much better using the standard rulers that you have for this than from the luminosity distance supernova. This is easier to talk about. It's simpler. Talking about the angular diameter distance requires knowing a bit more cosmology. So eventually I had to get to this. I'm going to talk a bit about the CMB. Okay? I don't really want to talk about the CMB physics in detail because that's a whole topic for a whole lecture course that I don't have time for. But I will just try to extract the sort of most important things in a kind of approximate way. In particular, what I would like to describe is this first peak of the CMB, because that's a scale that people use exactly to measure the angular diameter distance there. Okay. So what we know, let me be completely naive for the moment and say, so what we know roughly is that in addition to objects which see in the universe, there's also this background in the microwaves. It's at 2.7. It's at 2.7 Kelvin. There's a sort of perfect black body measurement. There's a perfect black body that's sitting out there, and the frequencies around the millimeters, which is exactly around microwaves. So this is measurement. You can see this is a kind of old-style plot because this measurement is still from Kobe, which is 1990. And this is still the best measurement of the black body nature of the CMB. So this is not the anisotropies. So which I'll get to in a second. So this is really just a statement that if you look at the microwave background, it follows exactly the Planck distribution or the Bose-Einstein distribution for a massless field. So with some particular temperature, this temperature is this 2.7. Okay? So what is this thing? Let me talk about it like this. So we have the CMB is some black body with a temperature today of 2.7 Kelvin. And the reason it's like black body is a little bit accidental. So I will just say this because I always found it quite interesting. So, in order to have things that are sort of have nice equilibrium states like this, so that's what black bodies are, they're just all sitting there in equilibrium for a long time, you actually need interactions. Now, if you think about the universe today, the photons are coming from some redshift of 1,000, they're coming from some huge distance, they're not really interacting. If they were interacting, we wouldn't be seeing the CMB. So why is this a black body? It turns out it's a kind of accident. So so the distribution, right? So what happens is the following: the universe at some point is very hot, and the photons are interacting. Now, the interaction of photons is in fact not with themselves, because that is extremely suppressed, right? So if you think about it, I mean, they're not charged, and electromagnetism requires a charge in order to have this Thomson scattering. So the photon by itself cannot interact with another photon unless it has an extremely high energy, which is of the order of essentially the mass of the electron. So about 500 keV, they can do it, but not below that. But there's a plasma, so there's all these charged electrons and protons, which are much less relevant for this, in a soup. So everything's ionized, and the photons are interacting with this charged plasma, and therefore equilibrating. So at some point, at some large redshift, and we don't know what it is a priori, so there's just some surface. So we know now, after we've measured this, to be a redshift of 1100, roughly. So if you think this is where we're sitting, so here I'm drawing this. I don't know. I only know redshifts, and I know distances if I've measured distances. So for me, I'm using as my time axis, I'm using this redshift. So as I go further out, I'm just this sphere, which has some redshift. So the galaxy is over here. So there is a moment in time, if you go far back enough, that everything is ionized, and all the photons are interacting with each other. Okay, and they establish a Planck distribution, right? So essentially the energy density there for photons when they're on equilibrium is something like this, where this eta is nu is a frequency, with F the Bose-Einstein distribution, right? So it's e to frequency over kt plus 1. There comes a moment in time when the peak of this distribution, so this peak here is, this is a 10 to the minus 3 electron volts. This is very low. But when this peak of this distribution shifts to be below the temperature of ionization of hydrogen, and at that point the photons no longer have the energy to ionize hydrogen, and there's a process during which the hydrogen atoms recombine, the universe becomes neutral, and after that interaction ceases. So roughly what you have is a situation where this distribution function is established during the time when the baryon and the photon fluid are tightly coupled and they're strongly interacting. Then the energies, the average energies, shift below that. And after that, what actually happens is the photons just propagate on null geodesics. This is what we were talking about yesterday. So if you take one photon, it just goes from that point on over here, and it just goes on some null geodesic. Okay. Now, when it's doing that, its momentum is redshifting as 1 over A. Okay, so essentially, this nu declines as nu divided by A, the scale factor. This is nu 0. There's some nu at, let's call it nu star. Sorry, let's call this nu star. There's some frequency that it had when it was emitted, and then it keeps on propagating. The universe is expanding, and this frequency is redshifted. Now it just happens that if you look at this distribution, if you shift this nu as 1 over A, remember you're just redshifting momenta of photons. They're not interacting. They're not reestablishing equilibrium. There's no reason a priori for them to follow any sort of real standard distribution in physics. But it just happens that because there's no scales here apart from this particular factor, that by shifting as 1 over A over here, you just rescale this Planck distribution as if the temperature was scaling as 1 over A. Okay? So what what's really happening is this distribution remains of the same shape. It's moving down to lower frequencies. And if you just measure at any point in time, it looks like the standard Planck distribution. But the temperature, which is also proportional to 1 over the temperature at emission, the last moment when they were in equilibrium, divided by the scale factor. Okay, so this is really it's a sort of important point because it's kind of, it's just, you shouldn't really think of the photons being here as sort of actually being interacting, establishing some sort of distribution and so on. They're really not. They're just individual photons probing the null geodesics of the space-time. And all the effects that occur that we can measure with photons, we can only really understand them just because we're understanding these null geodesics. Okay? So this remains a Planck distribution. Okay. So good. So essentially, this occurs roughly when the temperature, so you go through this recombination and the universe becomes neutral. Of course, it takes some time. This is not a step process, but it roughly occurs. So this temperature of recombination is roughly 1 electron volt. So it's significantly below the ionization energy of the hydrogen. So there's a process by which it takes time for this thing to really stop. It's actually quite complicated physics. And there was a lot of discussion over how exactly it worked and in the 60s. People were never sure that you'd actually ever see the CMB anisotropies. Okay, so this tells you that there's some sort of component in the universe that looks like radiation that seems to follow this Planck distribution. Okay, and the important, so one more thing I should say. So on this, so the other thing we know is that, so the universe at redshift more or less 1100 over here becomes neutral and photons propagate. But actually this is not true at for all times. So at some point, stars light up. So structure begins to collapse, nonlinear form, nuclear burning begins. At some point, you end up actually with a situation where most of the gas in the universe becomes charged again, because it's no longer is ionized again. So again, this is not something we know a priori, but this we know now. This is there's a reionization redshift, which is we've measured to be somewhere around redshift 8. So things are really moving on geodesics until about redshift 8, and after that, in principle, there's some secondary effects. So in principle, the photons themselves get scattered and so on. This actually erases a large part of the power in this cosmic background structure because of interactions here. But we sort of understand it, so we're able to measure this effect and take it into account. Okay. Yes. You mean does it affect this, for example? So there's two things, right? So there's this, which is the distribution, and there's a separate issue, which is the variations in the temperature, right? So what happens, it sort of rescatters photons in a way to remove power from this. But they remain to a very large extent, as far as we've measured to this. But of course, then there's all these plans to build satellites to measure this much more precisely. And this is when you end up with distortions of the spectrum and interactions with so actually, okay, let me say something more. So in principle, if I look at this, sorry, I will say what this is in a second, but just to answer your question quickly. In principle, there are clusters hiding here, right? And the way you know them is because they don't have exactly the same spectrum, right? There's this Y distortion. So it changes the distribution a bit. Okay, so in reality, the picture is a bit more complicated than this because the universe is not perfectly smooth, right? So there's structure. So there's something that we'll see if I talk about it. But there are perturbations that are seeded at the beginning. We think through this mechanism called inflation. And there's through gravitational collapse, they evolve in some particular way. So this surface is actually perturbed. And what we're seeing is we're seeing the sort of photons coming from this perturbed surface. Okay? So when you actually measure the temperature with enough resolution to see, small structure, you see that it's not exactly, 2.7, but this temperature varies by 1 part in 10 to the 5. But each of these little guys, if you just look at the spectrum, is a perfect black body at a slightly higher temperature, up to some effects that I was just talking about. So this is essentially the map of the sky with the galaxy removed, so it looks much better than it is in reality. That was created by analysis of the data taken by the Planck satellite. So there are these anisotropies, and this tells you about the deviation of the universe at this point away from this FRW, completely symmetric system. And we have an extremely good theory for really how to understand this pattern. But what I will care about, at least for now, is the fact that there is a characteristic size of these fluctuations. So some of them are a bit colder, some of them are a bit hotter. The temperature is a bit higher or lower. But there's a characteristic size, which is about 1 degree. Okay, so you see that if you take a Fourier transform of the sky. Remember, it's on a sphere. There's some spherical decomposition to do. So actually this one. So there's normally you do it in these multiple moments. So this is really you're just taking taking Fourier transform of a sort of to follow what Max said. I mean, there is a finite domain. So in fact, you don't have an infinite resolution, but there's this decomposition, which is in terms of some integer L of the multiples. And you see that it looks something like this. And for the moment, what I would like to discuss is this peak. Okay. So about 1 degree in angular size, which is multiple moment about 200. And this is not, this is a universe-dependent statement, right? So it's not like inflation produces a peak at 1 degree. This is a, as I would just show you, there is it's a feature which we in principle know the physical size of, comes from some physics in the early universe, and we're viewing it through the rest of the universe, from this redshift of 1100 to today, and therefore, since we know the physical size, we know the angle, we can work out we know what the angular diameter distance is. So let me talk about that. So to do that, let me do it like this. So what is the first peak? And again, I will cheat a little bit. This is a much simplified calculation. So what happens is that, let me just say something, one more thing. So this recombination happens at redshift of 1100. Matter radiation equality is at about, so this is Z star, this is recombination. And there's matter radiation equality, Z equality. So this is when the universe is half radiation, when you're scaling the energy density like this. And half of it is is dark matter or other baryons and so on. This occurs at about a redshift of 3,500. Like, I can't, it's something like that. So, which again, it's some property that's measured. Again, this is a universe-dependent statement. The more dark matter, this would be a different number. So it's not fundamental in any sense. But the issue is that when I'm discussing what happens at around redshift 1100, it is not true that there's no dark matter around. In fact, it's already quite a lot of it. If you go back to the very early universe, because dark matter just scales like the volume, while radiation scales as, I didn't really write this, we can see that scales as frequency to the 4 or temperature to the 4. So this is some Stefan Boltzmann constant times temperature to the 4. So it's really scaling like the scale factor to the power 4. At some point, there's, today there's practically no radiation. In the past, there was only radiation, only relativistic species. At some point, they reach equality, and you can't ignore one and the other. And the production of this is exactly at that point. So I will ignore the existence of dark matter for the moment to basically calculate this peak, but this is a bad approximation. Okay, so bear this in mind. But like I said, I don't really want to do a full study of exactly all these, this whole structure. So what you do is you say that the universe is slightly perturbed. So before we had the FRW metric, which was just a function of coordinate time or of conformal time, as I have it here, and all time, all slices were completely smooth. Now you introduce some perturbations, and which are position and time dependent. So d tau squared plus a squared tau squared, and then 1 minus. So you can show that in the metric in general, there are, so I included, good, thank you. Yeah, shows you, and I don't think about conformal time that much. So there's some, and then this is, okay, let me write it, dx squared, just like that, some vector. So if I write down some metric g mu nu, I can decompose it into scalar tensor and vector perturbations. And the tensors are the ones that gravitational waves, so that's very relevant, but not for this discussion. There are vector perturbations which sort of represent how the universe is sort of vorticity, essentially, how the universe is rotating. So that's something that isn't really only produced under very special circumstances if you actually have a vector field sourcing them. And apart from electromagnetism, there isn't really one that we know of. So the ones that dominate the discussion are the scalar perturbations. Okay? And I've picked a particular gauge. So this is called the Newtonian gauge because things look most like they do in Newtonian physics. Most codes are not written in this gauge. They use synchronous gauge, but unless you think in synchronous gauge all the time, it's sort of unclear as to what it's not very intuitive. So I will remain with this because this roughly looks like what you expect in Newtonian physics. So two of these potentials. And okay, so this is what the metric will be. So I will essentially expand the metric to linear order in these. So there's a background to do with the scale factor evolving, and I'm going to expand the metric to linear order in these guys. And then there's some sort of source for the actual energy momentum tensor, which is mostly going to be photons. So some radiation fluid. So radiation is defined by, on the background level, remember you're scaling as a to the minus 4 over there. So that means that pressure is equal to 1/3 the energy density on the background level. And you have, because you have these fluctuations of the potential here, you also have fluctuations of the, that actually source this. So there are fluctuations of whatever is sourcing the metric in the curvature, so the fluctuations of fluid. So there'll be fluctuations, and for something like this radiation fluid, they're defined by essentially in hydrodynamics that the pressure fluctuation is related to the density fluctuation by some sound speed parameter. Okay. And there is an addition to this. So of course, we are writing down T mu nu at first at 0th order in the background. I said it's just diagonal. Whatever the theory is, that's the theory for your matter, this is just diagonal. If you write down the T mu nu at first perturbative level, you actually have to worry what goes in there. So, there's the density perturbation. So this is a roughly a matrix, right? So there's a density perturbation here. There's going to be a pressure perturbation along the trace of this. And there are velocity perturbations that I can write down as rho plus p times some, it's a vector. So let me do it, a scalar perturbation, so di times v. So there's some scalar potential for the velocity that sits over in this part. And then there's a bit here, which is called the anisotropic stress. So there's a scalar perturbation that is inside this that looks like this, it's the traceless part of this energy momentum tensor. I can rewrite, so there's a bit that's the tensor itself, that's really the gravitational wave, or that's sitting here. There are vector parts of this bit, of the spatial part, and then there's a scalar bit that I care about here. So that requires me to have the scalar is just some potential. I take two derivatives to get the structure to populate this bit of the energy tensor. So this exists in general. So again, now in order to really discuss the theory of matter, you have to have some theory for how you relate pressure and density perturbations, and you have to have some theory for how you relate what the anisotropic stress is. So let me make the following statement. So in general, if you have this, that means the thing is a bad fluid. Okay? So fluid approximation is in some sense the statement that roughly the important part of the energy momentum tensor is really lying along the pressure density part here and some momentum perturbation. This is second, this thing has two derivatives acting on it. So really I can discuss fluids. It's a sort of to talk about fluids, they're an approximate theory. They're approximate theory where I do an expansion in exactly in these derivatives. It's called a gradient expansion. And if these guys are small, I can essentially cut it off at some point, and I roughly have something that is what's called an ideal fluid. And they are small if the fluid interacts quite well. Okay, so if there are many interactions, what's sitting over here will equilibrate itself and become just a sort of pressure perturbation. But if there are very few interactions, so there are then, remember this is some averaged object, so there's really some particles sitting underneath this, and they're scattering off each other. If they don't really interact, then I create some momentum and some shear, and this thing will remain because there's no interactions to sort of make it stop. So if there are few interactions, then this is a large quantity relatively and important. So if you look at neutrinos, which are also some relativistic species, which are also important in the early universe, and I'm also ignoring them, they have a large anisotropic stress because they don't interact. They're really not a fluid. This is why if you ever thought about this before, you have to do this whole Boltzmann hierarchy when you're looking at neutrinos, because it just doesn't get cut off. So there are higher and higher order terms and derivatives here, all of which are large. But photons in this kind of plasma with the baryons, of the charged electrons, in fact interact very frequently and therefore equilibrate very well, and therefore this is essentially zero. Okay? So a photon fluid doesn't have this. Now, have you ever thought, so light moves at the speed of light, right? So the speed of sound for the photon baryon fluid is 1/3. Have you ever thought about why this is not the speed of light? I mean, it is, right? Because this is true. You know that. This just comes from distribution function. So you have to really think about what you're trying to describe here. So I will get back to this later. So because for another reason, but I'm not describing here the density of individual photons, which themselves move at the speed of light. I'm describing large coherent perturbations. I mean, we're talking about things on the scale of the universe. The large coherent perturbations in the distribution of the photons. Together with the electrons and the which they're interacting, they're kind of, and those are sound waves. This is not the electromagnetic wave, which moves on a large geodesic. This is not the individual photon, which moves on a large geodesic. I'm describing sound waves inside this thing. And now depends how you think about this. If you look at electromagnetism, there is no sound wave there. The sound wave is defined as a scalar perturbation. There is no such thing. I told you there's a gauge freedom in electromagnetism. Get rid of the scalar. It's not physical. So it only appears if what you consider are not individual photons, but you're averaging over a distribution. And it's the distribution itself which contains these these fluctuations, these sound waves, the pressure waves, which are moving longitudinal waves. The longitudinal waves, the photons, electromagnetism doesn't have longitudinal waves, right? The longitudinal waves which move at the third of the speed of light. Well, square root of, right? It's 1 square root of 3. Okay. So anyways, we don't stress this often enough, I think. And let me do one more thing, which is that, remember what I'm trying to talk about is a photon baryon fluid. So it's not just photons, there's also electrons in there, protons and so on. Now those are pressureless. Okay, so they have a density, but they don't really have a pressure, they're slowly moving. And this thing is somehow coupled together very strongly because they're scattering on timescales which are much, much shorter than the timescales of the evolution here. They're sort of collectively moving together. So if you add to your pressure perturbation, well, this is just the photon part, but if density perturbation is photons plus this non-relativistic part from the baryons, what you get as an effective sound speed for the fluid together is in fact reduced by a factor like this, which is something like that. So the fact that I've added the baryons in there, in fact, they increase the density of a part of the fluid without increasing the pressure. So what I would call the effective sound speed for this thing is in fact reduced a little bit. And I will be discussing the sound horizon as being responsible for this peak, and therefore it's important to include such corrections. So they're included in the standard discussion. So I just do it. It's called baryon loading. Just say this. This thing's called. And again, this is a thing that is so there's more because of redshifting, the photons relatively begin to become fewer, the energy density in photons as compared to the baryons. So this is a thing that in fact increases as a function of time. So the very early universe is completely irrelevant, but it becomes relevant here in the close to the time of recombination. Okay, so now what I would like to do is to try to discuss the dynamics of this fluid. And the reason I say dynamics of this fluid is that general relativity does not contain a scalar degree of freedom, right? So if I'm in a vacuum and there are no perturbations of any fluid, this phi and psi are exactly zero. They're just not there. Okay, and I will write down the equations, Einstein equations at first order in cosmology, and you'll see that that's true if you don't believe me. So when you say that you're discussing, as we always do in cosmology, we're really observing things to do with curvature and therefore things to do with phi and psi. But in reality, the dynamics of phi and psi are not really the dynamics of the gravitational field. They're really dynamics of the fluid itself sitting around in a gravitational field. Okay, so I will derive an equation for phi, but it's really underneath that is the fact that there's some fluid that is perturbed and that those perturbations are evolving. Good, so I have Einstein equations, right? And I can plug in this metric that I have over there. I can plug in these fluctuations of the energy momentum tensor, and expand this whole thing to first order. And from that, I get essentially, since I'm looking at scalar perturbations, I get, well, in general, I get a time-time part, time-space, and space-space. And then space-space, I can do exactly what I did here. I can divide that into the trace bit, and I can divide that into the off-trace part, the shear part. So I get 4 equations. Laplacian of phi. This is in conformal time. So I've simplified life for myself by doing things in conformal time. Let me just sort of say, define that. So conformal time is here, and I will call the curly h, I will call that the derivative with respect to conformal time over A. So it looks like it looks like the Hubble parameter, but in fact it's not exactly the Hubble parameter, because remember, Hubble parameter is A dot over A. So there's a relative, so in this coordinate, the Hubble parameter, in this time coordinate, it's A prime over A squared, because there's a difference in the definition 2 times. But what appears all over the place is this curly h, which if you want is equal to A times h. So there's the momentum constraint, sorry, the Hamiltonian constraint, so the 0-0 equation. And delta I've just defined to be the density contrast. There is the vector part, so the spatial part, the spatial time part. So there's a derivative in space of this, and that's equal to half of rho plus p times the derivative of this velocity potential, exactly what I wrote over there. There is the trace part, plus h squared phi is sourced by the pressure, so a squared delta p, and this delta p I can just rewrite immediately as a squared cs squared delta rho. And there's the bit which is the trace part, so di dj minus a third delta ij delta squared. So this is a traceless part of the space-space part, which is exactly this pressure times, again, this derivative operator di dj times this anisotropic stress, which is 0 for a perfect fluid, which the photon-baryon fluid is. So I have these equations, and well, the structure of them is such that I can either write down an equation for the density contrast delta, eliminating all the potentials. So phi is equal to psi, so that gets rid of half of them, and then you can combine these two to get rid of them. Or much more simple for my purposes is to get rid of this delta and this delta p by combining things properly. And when you do that, you get an equation for the evolution of the potential, phi. So plus ts squared, and I guess I'm missing an h here. Minus cs squared Laplacian phi plus h prime 1 plus 3 cs squared h squared times phi. Roughly all I've done is I've substituted for this delta from this equation, combining them together. So cs appears all over the place. So you get an equation like this, which is a closed equation, second order differential equation for phi, for the 1 degree of freedom. But remember this doesn't mean that there's dynamics in the gravitational field, really. It means that there's dynamics in this fluid, because if I set this guy to 0 and this guy to 0, what happens is that the only equation you get is that Laplacian of phi is equal to 0 exactly. So there's no potential. So, and let me rewrite this. So there's h squared and there's h prime. H prime is the derivative of h. So you can in fact just rewrite this guy, which is a mass term, as 3h squared w minus cs squared. Okay, so if this were just photons and cs were exactly 1/3, this is exactly 0, because 1/3, 1/3, there's some small correction here, but it's not going to be very important for us. Okay, and I can solve this. In fact, you can solve this exactly, but I'm not so concerned about that. Okay, and remember, so the thing I've forgotten about, I've lied to you about, is the fact that there should be additional sources here, which are the fluctuations in the dark matter, and I've completely ignored them. But if you were to do this properly, you would have to include them. So this is an equation which is valid exactly in the very early universe, and then as you get closer to recombination, it stops being valid. So let me do the following thing. Let me take a Fourier transform. So my Laplacian goes to k squared. And let me just try to find solutions in two limits. So the relevant scales here, so I don't know how you think about these things. I look at some equations like this all the time. But there are essentially time derivatives, which are of order h. They come like this. These are also all of order h. And then there's this term, which is Laplacian, which is, when you take the Fourier transform, you get this k squared. So there's a change in behavior when k is of order h. So this is called the mode entering the horizon. So this is when the fluctuation is the size of the horizon, which is the universe, which is at that point in time. So if I take k much less than h, and let's ignore this correction to cs for the moment, I essentially get that phi, there are two modes. Phi is either constant, so this mass is exactly 0. So it's not exactly 0, there's a correction. It's approximately constant. And there's another mode which is decaying as the conformal time cubed. So if you've seen statements such as the curvature perturbation is conserved outside the horizon, this is nearly, although not quite, that statement. So if you look at this equation, for modes k, which are much, much larger than h, so the perturbations are much larger than the size of the horizon, essentially this Newtonian potential doesn't evolve. And there's another mode which decays, which you can just forget about. It doesn't matter in cosmology. And then when k is much larger than h, you get a solution which looks like some amplitude, some decay in tau minus 2 times. So again, if this were exactly 1/3, this is an exact approximation. Since CS is not exactly 1/3 but evolves in time slightly, there's a small correction to this, but morally this is a correct statement. So as you go inside this horizon scale, you begin to oscillate. So this mode is constant, and then it begins to oscillate. So really what is happening is that the fluid, this photobaryon fluid, can only respond on time scales which have to do with the sort of time it takes for information to cross, right? So there's a speed of propagation of these sound waves. So if something hits the blob of this fluid on one side, it's not going to be able to respond on timescales much shorter than it takes for the sound wave to propagate. So this side doesn't know about the fact there was some impact until the time equal to the sound crossing time. So what's happening is that when you have a very large perturbation, which is much larger than the size of the sound horizon, so it's the CS here, the universe, I mean, this fluid doesn't know that there's even a pressure. So it's just collapsing. So the very interesting thing is that at these very large scales, despite the fact this is a fluid which has pressure, it can respond with force to an increase in density. At very large scales, it's not actually happening. It's really just collapsing together. So all the species are collapsing as if they are really, as if they were just not, pressure free. And the effect of that is that the phi is a constant. Okay, so, but then when you reach the sound horizon, so you reach the scale at which the information can propagate. So I should have maybe written actually CS here like that, because this is really the relevant. This is really the relevant guy. So when I reach the sound horizon, it begins to oscillate. Okay, this one particular mode begins to oscillate. But if you were to do the Fourier transform of this with some initial top hat or something, you would see that, just kind of this thing grows, and then it sort of just rests itself slowly and then begins to dissipate as the universe expands. That's actually really what's happening in physical space. So there is an oscillation. It has this particular frequency. And essentially, the peaks here are exactly at the nodes of this frequency. Not nodes, the maxima and the minima of this frequency. Okay. So this first peak is exactly when this phase is whatever it is, pi by 2, pi. Sine goes. So whether it's sine or cosine is I guess I should have been more careful, but whether it's sine or cosine is a question of initial conditions, and actually really solving this properly, I didn't want to write down the solution to the Boltzmann equation, the Bessel equation, which is what this is, and then to do some expansion. But in principle, there's some appropriate initial condition super horizon, which sets some particular phase for this. But the separation of these guys is pi. So therefore, that what's happening is that at the time of recombination, this is the last moment, you're seeing the picture of the universe at the time of recombination, then propagated forward to you on all geodesics. So at the time of recombination, the scale at which this happens is when, so this is this tau star over here, it's when this guy is pi. And therefore so now this guy, of course, is a slow function of time, and so on. So really, the fundamental quantity that you're really dealing with here is that there is what's called a sound horizon. It's really a distance, which is some integral of this CS d tau between the beginning of the universe and tau star in recombination. And roughly, I can even work out what this universe is roughly energy radiation dominated during this time. So I can rewrite this in terms of the redshift. I will get this factor of h, as I always do. So I can even, so there's a prefactor like this. H0 comes back, as always. And I can rewrite this in terms of, would have been h of z here divided by h0, or you can even write this as 1 plus z squared, because that's what's happening over there. So actually, let me do it like this, sorry. So just h of z. So there is a physical distance scale where this first peak, at which this first peak is imprinted. And is the size of the sound horizon. And now the argument is essentially that we know what happens in the very early universe. This is a thing I can compute. I know what h is going as 1 plus because what else could it be doing? Okay, there's maybe some correction. There's some correction I have to put into the CS, but I can roughly work this guy out, and so I can get this object up to this h0 again. As always, everything is sort of defined in terms of h0 in cosmology. And but the reason I'm telling you all of this is because this is the one moment in time when you can actually say something about not a so the reason why, if you think about this, the reason why h0 always appears somewhere is because you're always dealing with geometrical quantities. You're dealing with some sound horizon. You're dealing with some null geodesics. You're dealing with, there are all things to do with just angles in the sky, right? They're always just, they're always geometric quantities. You're doing cosmography, really. You don't know what the composition of the universe really was at any one point in time. You're just looking at some geometrical thing. So there's no scale to this. So I can just replicate the universe of a different h0, and everything will look the same up to this h0. But turns out that with the case of the CMB, there's one thing we can do to actually give us this thing as a number, as a dimension. So let me just to make this point. So this is the picture of the CMB. This is recombination. This is t equals to 0. So this is some magic that happens in the early universe. There's a sound wave propagating out at recombination. Roughly, the characteristic scale is this RS that the sound wave has propagated out. And I'm sitting over here. This is today. T equals t0. This is me doing my experiment. And I am seeing this as some angle theta star. And I know that theta star is equal to RS divided by the angular diameter distance. So if I measure this angle, I know what this RS is, I know what dA is. So in this sense, dA is still defined up to h0. Well, now let me break that. Let me break this. So one thing I haven't told you, or I haven't included in any of this, is the fact that we have actually measured the temperature of the CMB. I told you it's 2.7. It's very precise, right? So this is actually the only dimensional quantity we measure in cosmology. Everything else are kind of ratios of things. But we measure this temperature. It's a physical temperature. And therefore, if you include that, for example, you know that at redshift 1100, the energy density, so if you know the temperature, you know the energy density today, you scale that as a to the 4, you know the energy density of the universe at redshift, at recombination. And therefore, you know the value of h at recombination. So by including the temperature of the CMB, you, in fact, can make all of this dimensionful. Because you just know that h recombination divided by h today is the same as t recombination divided by t today. 2 power squared. So I measure my 2.7. And everything becomes dimensional at this point, and you can get this h0. So if you look at, let's say, so people don't worry about this so much anymore because so much has been sort of, the data are so precise that many correlations have been broken, and therefore people don't necessarily report it this way. But if you look at especially the older papers from WMAP from cosmology, they never gave you the big omegas. They never gave you omega matter. This is a derived parameter, if you want, because really what they gave you was a parameter omega matter little h squared, which they called little omega matter. And the reason for this is exactly that all this stuff in the CMB, because the temperature is to do with, so there's this equation, let's say air the universe, just rho radiation over m Planck squared. I can divide by 3h squared here to get this omega matter, right? So I get 1 is equal to omega, say omega radiation in this case, plus whatever omega matter, etc. So this assumes that I know what h0 is, but I can always, so what this little h is this assumption that you can assume that h today is 100 kilometers per second per megaparsec. So when h is 1, this implies that h0 is 100 kilometers per second per megaparsec. So this is a kind of weird unit. I've seen this, but it means that a galaxy 1 megaparsec away is going to be receding from us 100 kilometers per second. That's what the cosmological flow is. So, but since all of these are, this is really a t to the 4, which we know exactly what it was at the redshift of recombination. I know exactly physically what this guy is. So I'm only really measuring this combination unless I break the degeneracy. So it's the opposite problem, right? I need to break the degeneracy and get to my dimensionless things by measuring h somehow. So to combine both the late universe and the CMB in order to actually extract it. But the CMB essentially allows you to measure, because you know the temperature, allows you to measure dimensional. But then relating to the dimensionless ones is the problem, and then you need to do some combination of data with the late universe. Is it okay? All right. So there's this peak. So this peak. So this peak is an anchor. So if you want the way to think about this, the way you think about this typically is that you say, look, in terms of, let's say, analysis of data from Planck, is that you will anchor the cosmology in such a way that this appears at 1 degree. There's some, and then you propagate it forward using supernovae to today to get all the parameters, all the cosmological parameters. But this peak is an anchor at redshift 1100. So can we do better at lower redshift? Because really we would like to somehow get rid of our dependence on the supernovae, which we may or may not believe in. So it turns out that this peak reappears also at lower redshifts in something called the Baryon acoustic oscillation, BAO. And roughly the statement is this. So in this universe, at recombination, there was an excess of power on some particular scale due exactly to this, the fact that the sound horizon was had this node, had this peak. So the sound wave had a peak exactly at that particular scale. Now this was the photon baryon fluid together. As the universe kept on expanding, the photons basically they disappear, but the baryons sort of remain with some part of the structure imprinted in them. Okay, so they're just, so remember this is a correlation. So if there's a peak in one place, there's likely to be a peak 1 degree away on the sky. So roughly, if you have a baryon peak in one place, roughly there's another baryon peak, once the photons have gone away, at the sound horizon distance in the later universe. Now this gets processed, so of course this is not quite so simple in that these baryons, they have the velocities, they keep on moving, some of the signal disappears, but in the end, if you look at how the galaxies are located in the sky, you will see that there is such a thing. So this was detected in 2007 for the first time. And for this, I need to tell you about galaxy correlation function a little bit. So, okay, let me show you a picture. It's easier to understand. So really, most of the time, what we spend time doing in cosmology is making maps like this, right? So this is in the late universe. Each of these dots is a galaxy. So this is from the SDSS survey. So each of these dots is a galaxy. A map, and you say, look, the galaxy happens to be at this angle in the sky, and you look at its spectrum, and you can establish what its redshift is. Now, there are many. This is a very expensive process. So getting this redshift exactly is a pain. So if you want to do lots of galaxies, then you take pictures with many filters, and you roughly get this photometric redshift, which is always biased in some sense. But what we have managed to do is to get a significant part of the sky up to some redshift of order 1, let's say, mapped in terms of the location of the galaxies. So once you have this, you can start asking the question. It's like, if I pick one particular galaxy over here, what is the probability that there's another galaxy separated by some distance? Okay, so this is a, and even if there is no, so roughly this is, if you just have them distributed randomly, this is a Poisson process, right? So they're just Poisson distributed, right? So there's just some average number. So if I look at any point in the survey, there's some average density of galaxies here, and the number in any particular pixel that I pick is related to the Poisson probability with that particular mean and variance. But turns out that this is not the distribution the galaxies follow. They're not Poisson distributed. It's not random. Turns out there's a structure to the way that they are distributed, and this is what people call clustering. So if I define the probability of, so I pick one galaxy and I'm looking for another one. Let me just do it like this. There's some mean density of galaxies. Okay, so if I just say, look, pick one galaxy, and what's the probability there's another one? That's related to this mean density of galaxy in some pixel. So there's a mean density in this pixel. That's n. There's a volume element, right? So this is my pixel size. There's a volume element, there's a density, there's a volume. And if this were just Poisson distributed, it would be 1. But I will call this correction to that the 2-point correlation function. And it's a function of separation. So I've made an assumption here, which is that this thing is purely a function of separation. Okay? It's not a function of direction. It's not a function of a particular vector in the sky. So the reason I can make this assumption, I believe, is the Copernican principle again. Right? So the universe is the same in every direction and is the same everywhere. So for this, I believe that these 2-point correlation functions, in fact, just a function of the scalar separation. This is not true. Okay. But I can do that, and I can plot it. And the origin of this curve is well understood. We'll see how we go. I may talk about that. But the important part of it is that there is this peak over here. Okay? So it doesn't just fall off like that, but there is a bump. And this bump is exactly some processed version of the CMB, of the first CMB peak, at the redshift, which I'm looking here. And I just made this sort of statement which mixed different things, separations, redshifts, distances, and so on, and you should worry about this. Because what I'm plotting is angles versus redshift. In order to say that this is a separation of 150 megaparsecs, I really need distances. So what I'm trying to discover is distances, and I don't have this to measure this. So normally the way that you do this, in fact, is that you, in order to, so look, so I have this map, and I would like to pick, I want to measure this psi, right? I want to measure the correlation function. So I would like to pick one galaxy, this one, and then figure out how many there are 150 megaparsecs away. So what exactly is that on this map? So I have angles and I have redshift. And to convert angles and redshift to distance, I need a cosmological model. Okay, so actually I need to put in, by assumption, some cosmological model in order to convert separation, for example, on the sky, an angle at the same redshift, into a distance, or perpendicular to this. So a difference in redshift in the same, if one galaxy is nearly behind another one, so exactly I wouldn't be able to see them, but if they're nearly behind each other, to convert that into this redshift difference into a separation. So in fact, there is a very large discussion in cosmology in general of what are the good ways of actually really establishing what the two-point correlation function is. And the cheap way of doing it is that you really assume some cosmological model, then you find this correlation function, then you find this correlation function is not exactly a function just of separation, but it's also a function of some angles, and then you do some corrections to your background cosmology in order to show that it's homogeneous and isotropic. But there are smarter ways of doing it too, but forgive me if I... So there's an issue of the data analysis for these BAOs, which in principle, if you don't really know anything about cosmology, just would basically destroy this. But since we roughly know what the model seems to be, allows us to map angles and redshifts into this separation. So what I actually have is that I see at a slice in redshift. So I take a particular, I take a bunch of galaxies which are at some redshift. I work out some separations between these pairs. I establish two-point correlation functions at that redshift, and I find there's a bump. And this bump will be, if you want, an angle in the sky, roughly. Okay. So again, this establishes so there's a bump in psi, which is at some angular size at some redshift. This is, let's say, a model-independent way of doing this. But so there's really some angular scale at some particular redshift. Since I know this, and I also know physically what this is, right? Because physically this bump is exactly the same sound horizon that I calculated already. Then I know that if I multiply this by, no, it's the other way around, right? I know that the angular diameter distance to the redshift is equal to the sound horizon over the angle of this BAO at this redshift. Okay. So again, I can work out an angular diameter distance like this. And because you're measuring millions of these galaxies, so the sort of number statistics are very good for this particular feature. You can really slice the data into redshift slices, roughly, and in principle establish this angular diameter distance as a function of redshift. Okay. So is this combination of things which if I talk about this, then yeah. So it's this combination of things that essentially allows us to be sure that this acceleration that we're seeing here is really happening. So, okay. Roughly, these are various surveys where the BAO feature has been seen. You can see that the data has been divided into redshift bins, and they measure the distance, angular diameter distance to this feature, and let me not mention why there are three of them. It's a question of the type of whether you're looking transverse or parallel, but not to worry about that. Point is that roughly they seem to lie on this curve that is expected of lambda CDM. So, and they roughly lie in this redshift range that, in fact, is also covered by the supernovae. So we've established this duality of this relationship. They're not labeled on this plot. I don't know, actually, I don't know what they are. Yeah, one strand, so some of them are, I don't know. You can look in there. But if you do that, so this is now from Planck. This is now from the Planck. So again, if you do that, you can in fact take a derivative of this distance. Remember, this distance is some integral over 1 over h. So I take a derivative of this distance. So this requires, of course, taking derivatives of data is horrible. So it has to be very good. But take a derivative, you can really measure h. Okay? And so this is h divided by 1 plus z. So it has this funny shape. And you can see that, okay, so with Planck, you measure some sound horizon. You establish that it's this 150 megaparsecs because of what our discussion was. You then bring it forward. You see that this sound horizon appears in these here, so the distances, they match. So h is, in fact, roughly as predicted. So this is a different technique of measuring. This is, it's a little bit off, but people argue whether that's a significant difference at high redshift of these distances, but we can talk about that if you want. But roughly things go through, whatever the error bars you expect. But this measurement is completely off compared to what this is. And this one is really trying to measure the recession velocity from local supernovae. So let me, and this is so this difference is exactly what's called this H0 tension. So let me just say a little bit about this. So this is in fact right now the biggest problem with the lambda CDM model. And then tomorrow I will discuss the things you can try to do to fix it, and then how gravitational waves would help us. So really this measurement is extremely complicated and yet very traditional. So what you're trying to do is so this Riess measurement. So Adam Riess, Nobel Prize winner, he was one, he was on one of the teams that discovered the acceleration of the universe, and has been measuring this, has been working on supernova and trying to measure H0, the last 20 years. So what they do is this traditional, so you would like to, the problem we had with supernovae is that we don't know what the absolute luminosity is, because we don't really know after you standardize, once you standardize, you don't really know what the supernova looks like. You don't really know what it would be if you're right there, how bright it would be. But for local supernovae, you could in principle know, no, so let me not say it differently. So local supernovae, you can actually really measure the distance by building a distance ladder. So imagine that you have some star which explodes in some galaxy nearby. So this is us sitting over here, and there's a galaxy nearby. So you can measure this thing. You can measure the light curve of this supernova here. You can do a standardization procedure on it. But because it is so near, there's in fact some hope for you to really measure the distance. Now, the simplest way of measuring distance, but this only works for objects inside our galaxy, is to measure it by parallax. This is really, you say, you look at where something's in the sky, you wait 6 months, the Earth is on the other side of the sun, the position will have shifted with respect to the stars which are much further behind, and you can really measure by doing trigonometry what the actual physical distance to this object is. But this really only works inside the Milky Way. So this is the Milky Way. I apologize for my excellent graphics. Now, if you would like to go a little bit further, you have to do something else. So they build a ladder which is based on the observation that there's a certain type of stars called Cepheid variables where there's a precisely measured relationship between so the stars which pulsate on, so they get brighter and they get less bright with some time scale. And in the Cepheid variables, there's a very particular type of object, and there's a relationship between the brightness, the luminosity, the intrinsic luminosity of this object, and the frequency from the time period of the pulsation. So you see them inside the Milky Way, and therefore you can measure the distance there to them using parallax, and then you see, therefore you know what the real absolute luminosity of this object is. It's just 1 over r squared. It's not cosmology, it's local. And you can establish this relationship, and then you apply it, because they're very bright stars, so you can reapply it in nearby galaxies. So you can observe these Cepheid variables in the host galaxies of where you've seen the supernova. Now we can't see a supernova here because one occurs roughly once a century in any galaxy. But once you go far enough away, there's a sufficient number of galaxies for you to have seen, some number of supernovae. It's not 1,000, it's of order 20 or so. Right? But you can really measure the luminosity, the apparent, you can measure the flux from the supernova. You know the distance because of this particular calibration, and therefore you really know the relationship between the luminosity and the distance. And because it is receding from you, right, there is a redshift. So when I wrote down luminosity distance, the equation was something like this: dz over h. For small z, which is all of this is, right? There's a very small z. I can relate. So we'll call it delta z, right? For small z, I can expand this expression, and the leading order contribution is this. So luminosity distance is really just inversely proportional to h0 with redshift, if you want the recession velocity being the appropriate parameter to put here. So by looking at the spectrum, you know exactly what this is. You know what the distance is because you've measured it like that, and therefore you can measure h0. And this is a dimensional measurement of h0. Okay? And doing this measurement of h0, you get this result that, where is it? So the claim now is, so of course this is a war between Planck and the recent code, because this has been, I'll show you in a moment, this has been disagreeing for a while. And this disagreement is only getting stronger, and they're putting out more and more precise claims as to the precision of their measurement. So they're claiming it's something like this. So it's a 2% precision roughly. And by doing this measurement of the CMB, looking at the temperature and projecting things forward, assuming lambda CDM, you get this Planck value of h0, which is 67.4 plus or minus 0.5 kilometers per second per megaparsec. And this is now 4.4 sigma away, is the top line number. So this is this gap. And they are measuring different things. Okay? So this is a problem. This is the big failure of lambda CDM. So either one of these measurements is wrong, or in fact it shows that something is happening different in the physics. It's a big difference. And oh yeah, sorry, I was going to show you not this. So it's this plot from Wendy Freeman. You can see that the CMB measurements of this have been consistently kind of low compared to the local measurements of h0. So it's a kind of thing that sort of has been there. and it's kind of evolving forward, and it's not really getting closer, even though precision is increasing. So this thing is called the H0 tension. Okay. This is the 2000. This is the one that he published, whatever, a month ago, 2 months ago. Yeah, yeah. He's officially saying 4.4 sigma.
Yeah. Right. Time for a few questions.
Mm-hmm.
It's about